Welcome back, guys. The Network Berg here. Hope you're doing well. This is the third video in the series for the MTCRE certification for MikroTik. And we're finally talking about routing. So routing plays a major role, obviously, in the routing engineer certification path because you need to understand how routing works. How do packets get from point A to point B? How do we actually make the solutions work? Because to me, routing has always been the most fun part about being a network engineer. It allows you to build roads. It allows you to see how everything traverses across a network. And it's just so accomplishing whenever you finish something or you set up a network and it works the way it's supposed to work. And it's really a nice feeling. And I hope that I can get you guys to understand routing a bit better, and then you can hopefully also implement what I'm trying to teach you in your own day-to-day lives, and then you can also see how cool routing really is. Anyways, let me stop babbling. Let's actually get into the video. See ya. All right, so let's discuss this amazing thing called routing. Before we get into it, I just want to say that I will be posting some reference material on the comment section that I'd like you guys to go over at your own pace as well. It will be from the MikroTik help wiki, and it's going to be very, very informative, or it's going to be good to supplement that with what I'm trying to show you in these videos, just to give you a better grasp or understanding of the routing process. Because I want you to understand that when we're talking about routing, we're in essence saying we want to figure out how to get from point A to point B. And routing just kind of like figures out everything in between point A and B, and it's actually a pretty interesting concept. Now let's talk about routing concepts. I've got a presentation prepared here. We'll just be reading through it. And I just want to say routing quite literally makes the world go round. It is because of routing that computer systems are able to communicate between networks and establish connectivity to remote hosts that are not on the same broadcast domain. In essence, routers have the function to stop broadcast traffic. However, it also forwards traffic out towards a gateway for any networks that are not configured locally on the router that exist in the routing table. So in essence, what that means is whenever your router receives a packet from any device, it will look at its routing table and it will then determine where it's going to forward that packet to the next gateway so that it can eventually get to its end destination. Now, any device that has network connectivity will have some form of a routing table to dictate how to leave the network or which network the device belongs to. And this is where I'm not going to speak like in third person, because even the computer that I'm using, that you're using, it has a routing table. So what I'd like you to understand is the entire function of the routing table is to forward datagram packets from one device to another in order for data to be deconstructed, or as we like to call it, encapsulated and decapsulated between networks. So in essence, the process of routing allows two endpoints to communicate and then form network connectivity. It is I don't want to say it's a basic human requirement, because it's not, but I feel like networking in its own has actually jumped or leaped how us as a human race has evolved. Because without computer networking, how would we have all of the access that we currently have? How would we be getting to stuff like Google to quickly figure out how to do something, or watch this YouTube video so that you can be instructed in something new? Without the internet or without networking in itself, we would still just be limited to having physical material on books and whatnot, which is a very slow way of accessing information. And I just want you to understand that this is one of the reasons I take great pride in my job as well, because I know how big the function is that we perform. A lot of people are in cloud and all that stuff these days, but it's what you as a network engineer does that actually makes everything happen. So be proud of what type of field you are working in. Right, enough motivationals. So I also want to talk about the MikroTik route selection process, because whenever the route or the packet actually comes into your router, there is actually a route selection process that is predetermined almost by the MikroTik to decide how a packet is going to get forwarded. Now, MikroTik makes use of two types of tables, namely being a RIB, or a routing information base, and a FIB, a forwarding information base. Now, I'd like you to think of the RIB as being the back-end database that's actually calculating everything. It's seeing stuff like which firewall rules are being used, which routing table a route might belong to, which protocols the route was being learned from, was the route statically assigned, is it the directly connected route? Those type of things are being picked up by the RIB, but it's not necessarily something that you're seeing or controlling in front of you as an administrator. You're just need to be aware of the RIB is in the back end basically figuring out which routes are the best. And what the RIB will then do is spit out a copy of its routing table into the FIB, the forwarding information base, which is in essence what we see when we go into the IP routes tab on a MikroTik device. So that is one thing you need to understand with the RIB and the FIB. And there will be more information in that documentation I'll be giving you as well. But besides just the RIB and the FIB, you'll also need to be aware of a few additional things, how routes are selected. Namely, if a route is directly connected on your router, meaning you've added an IP address and put it on an interface, that route will always be preferred above anything else. You'll see the route even is numbered as 0, I think. Might be, yeah, it's 0. Those routes, directly connected routes, will always be preferred over anything else. Next to a directly connected route, you might see stuff like statically defined routes, which is me as an administrator. I'll create a static route as a person. I'll type in where I want to go, and then I can tell the route what its gateway is, and then that can be used to route traffic. But besides statically assigned routes, we also get dynamically assigned routes, which is where we configure something like a routing protocol like OSPF, BGP, or RIP. And this routing protocol's job is to basically learn how routes work across the network. They each have a different way of achieving it, and they each have a different type of use, especially OSPF and BGP. But you need to be aware of, if you see a route marked with a D, that it's been dynamically assigned. All right. Now, besides the routing protocols, we're also going to be looking at route distances, because that will also determine which route is preferred. So a route that's maybe have a shorter distance, and it makes sense if it's not as far away, but you can set the distances, but it can also be determined by the routing protocols. A route with a shorter distance would typically have a higher preference than a route that has a longer distance. And then finally, we get the longest prefix match, which I'd say is typically the one of the first things that you need to look at when you want to see where the router is going to route the traffic, because all the longest prefix match means is if you get a packet, let's say for a host that is in a /24 network, but there's a route on your routing table for something for a /29 network that the host also falls a part of, then that /29 route will be preferred. So in essence, when we say longest prefix match, I'd like you to just think of, when you think about the network bits, which one is more like full. So if it's 255.255.252, which is a /30, that's typically going to be preferenced over something like 255.255.255.0 in the routing table. All right. Now let's just see. So here I've actually got a picture of the routing table, and you can clearly see you can access the routing table by going into your IP and routes, or you can just type IP route print on your MikroTik, and then it will spit out your routing table, which in essence tells you exactly what your router is doing when it's receiving a packet and it needs to forward that packet on. Because the routing table will have all of these line items, which will tell you what the destination address is, what the gateway will be to get to that destination, the distance. So again, the shorter distance is the one that will be chosen. And then you'll also get stuff like a preference source, but this is the pref source doesn't really factor in to if a route's valid or not. That's just, if you see a route with a pref source, it just means if you ping something in that subnet, the router will preference using the source IP to like get there. But that's actually something for its own discussion. What I'd like you to make aware of is the different types of fields that we get in here. And I'd like you to see the active routes, which are always marked with an A, and those routes will be dark in color or black. Then you have inactive routes, or blue, which means the router is aware of the route. It knows it exists, but it's not chosen. It hasn't been chosen by the route selection process. So it's now this blue route in the routing table. And then you've also got disabled routes, which is when you select the route, you click on the disable button, then the route will not be used at all. All right. I also want to make you aware of stuff like route flags, but we'll get to each of these things as we go through this presentation. So let's quickly discuss the route distance, which is that distance box that we showed earlier. So route distance are used as a metric to determine which route should be more preferred in the routing table. A route with a lower distance is generally the most preferred route. A new static route that is created will typically have a distance of 1 unless changed by the administrator, whereas a directly connected route will always have a distance of 0 as the network exists on the router and will never have to leave the router. Routes that are changed to .2 or 255 will not be routed at all. So think of that almost as a lot of people call that black holing a route. Now let's discuss the longest prefix match. So the longest prefix match refers to when having multiple routes to the same destination and the router having to make a choice based off of which route is best to the destination and will be chosen in the route selection process. An easy way to determine which prefix is the longest match is simply to convert the prefixes /24, /25, /26, etc. into subnet masks. The subnet that has the most bits in the host field is the route that will be selected. So that just means if you, that's what we were talking about earlier. So here's an example. You want to know where traffic will be routed for 192.168.2.30, and you have the following entries in the routing table. So here you know that these are all like a /24 is that whole /24 network, that class C. We've got a /25, which is just half of that network, and then we've got a /26, which is in essence just half of a /25. But if we look at what IP that is, we can see that it will typically fall under the /26. So it would mean that the route that I've highlighted in red here would be considered the longest prefix match and would be selected to route the traffic. It doesn't mean the other routes become invalid, because any hosts that are outside of this /26 would still be routed to whatever gateways are part of these other two routes. Now let's discuss the routing flags. So routing flags allows an administrator a way of quickly understanding how routes work on the routing table, as well as how routes have been learned. You will be able to view the routing flags being used by either hovering over it in the IP route or by doing an IP route print. I'll give you an example in that in real time as well. But in essence, I've just given you a little table here that explains if it's marked X or it's grayed out, it's disabled. A is for active, which means the route's being used. D is for dynamic, which means it's been learned either by a routing protocol or even by a mechanism like DHCP can also give you out something like a default route. S is for static, C is for connected, and then we've got our different types of routes there. Now, here I've given you the example of where you can find the routing flags to see exactly what they're doing. And now we can quickly discuss the routing protocols. So besides having to learn directly connect routes or static routes that we define manually by an administrator, routing protocols allow us a means of learning routes dynamically via routing protocols. So it is not required to understand how all routing protocols work for even the MTCRE. What you should understand is that they exist, but you will learn a lot about the OSPF. So this is actually the biggest change on this presentation between the MTCNA and MTCRE. Protocols that you will see used a lot in server provider and enterprise networks may consist of link state protocol, which is OSPF, as an interior gateway protocol, an IGP, which typically adds a route with an administrative distance of 110 and gives the route the O flag. All right. A path vector, which is BGP, is an exterior gateway protocol, EGP, which is basically used by the internet. It's how the internet works and learns all of our public IP addressing. And you'll see that that will have a B flag, and that works in a different like autonomous system. So it allows autonomous systems to connect with each other. OSPF actually also uses autonomous system, but you'll be working within your own autonomous system, in your own cloud, in your own network. And then we get stuff like RIP, which is a distance vector. And I'm going to be honest, it's very rare that you'll see RIP in a modern network. It might still be used in some legacy stuff or some very, very specific use cases. But be aware that RIP still exists, and all that RIP does is it looks at the hop count to get to something. But the issue with RIP is also after a specific amount of hops, like with your ICMP, it will just stop routing the traffic. And now we've got our default route that I'd like to be talking about. So a default route, you can think of this as a catch-all route, which simply put will be a route in the router that will be used to forward traffic if any prefix is not matched in the routing table. So that is our 0.0.0.0/0 route. If no default route exists in the routing table and there is no prefix for the destination that you want to route, it's just going to drop that traffic. All right, so here I'm just quickly showcasing how you can create a default route. And here we have a bit of an example of routing traffic between networks. But I'm actually going to close the presentation so that we can properly look at some routing concepts. And let me quickly explain my Eve topology here, because I've created this specifically for the MTCRE course. Everything we're going to be covering with the MTCRE, we're going to be doing in this topology on the routing level now. So all of our static routes, policy-based routes, ECMP, OSPF, those type of configurations, we're going to set up in this network, even the IP, EO/IP tunnels and all that stuff. But this will be our baseline, a template almost, that we can use, which is going to be nice. And what I've kind of set up here is I've got some routers in the bottom, and the routers marked as blue. Just think of this as the blue customer or whatever. These routers are within the 192.168.0.0/16 subnet, whereas my red routers are in the 172.16.0.0/12 subnet, which are private subnets, which is actually something we should be discussing as well, because I do want to make you aware of there is a difference between private and public IP addressing, because you don't want to make the mistake of adding public IP addresses and using them on your network as private addresses, because one day you're going to have customers, they're going to want to go to a specific site, and then your router will tell them, oh, but it's on me, the IP address exists on me, and then nothing's going to happen with that traffic. So always make sure that when you are configuring stuff in your own networks, that the internal side you keep with private IP ranges that are available for us to use. They're a very specific RFC for them. So it's a very specific standard. It's a subset of IPs that we can use however we want. And that being the 10.0.0.0/8 subnet. And I've already talked about 192.168.0.0/16 and 172.16.0.0/12. Those three big subnets are typically what you'll use for your private IP addressing. All right. So what we're going to be doing with this is these green routers will be basically emulating ISP routers, and we will be spanning specific services to our customers, which are in these little blocks at the bottom, and we'll set up routes so that maybe these customers stuff can get to each other. Maybe we can say there's a client like PC1 once it gets to PC6 because that's a web server. We'll set up stuff like that as well. And this is going to be a fun, relaxing, open course. And we're just going to have a good time with this. I'll firstly just be covering the routing table and how to set up some very basic static routes. And then in further videos, we'll be looking at doing some more of the complex stuff like the ECMP and the policy-based routing and OSPF and all that. All right. So first thing I'd like to do is actually get onto a MikroTik, this router one that I've got on the topology, so that we can look at a routing table in real time. So I'm just quickly opening up my Winbox, connecting to the device. And there we can see is the Winbox session. So all I'm going to do is I'm going to navigate to my IP routes. So here is router 1's routing table. And as I mentioned during the presentation, each router, each device, even the computers, they have their own routing tables. They are basically telling the device how to get to something. In this topology, this intranet that you see here, it is the actual intranet, but it's also my computer. So when we look at that intranet, if I want to get to any device on this network, I can use router 1 to actually get to those devices. Let's go back into the routing table. So my computer can use its routing table, and it will see to get to a network that I define, it can use this router 1 to get to whatever network. Now, router 1 on its routing table, I just want to go through some of these entries quickly, because here we can see we've got a bunch of directly connected routes. So they're dynamic with a D because I put it in as an IP address on an interface, and then the IP address field basically told the routing table, hey, this is a directly connected route, and it dynamically filled that into the routing table. It is active, and the C is obviously for connected. But I wanted to show you this route specifically, which some people get quizzed on a lot and they fail sometimes, because here you can see a dynamic route. It's active, but it's also statically assigned. So how the heck did that happen? So this type of route you'll typically see whenever we're using stuff like triple PoE or DHCP. The reason being, if we go into those options, so let me go into DHCP client. If I look at my DHCP configuration, and we can see here there's an add default route. So the DHCP obtain an IP address dynamically, and it is the protocol itself actually filled in the information into my routing table, but this add default route option also statically embedded it into my routing table. So this is why you'll see something like a DAS if you're using triple PoE or DHCP. But with other routing protocols, you won't see the S, you'll just maybe see like a DAB or DAO or stuff like that, whatever you're learning. All right, so what I'd like to do in this little exercise is I want to be able to get from the internet, so my computer, I'm going to use router 1 as a gateway, and then I want to be able to access all of these WAN networks that I've defined in my topology, which is these gray networks. So 192.0.0/30, 192.0.0.4/30, all of these types of networks. These two networks already exist on router 1, but I'm not able to actually ping them from my machine yet. So if I go in here and I just open up a new window and I type ping 192.168 or 192.0.0.1, I can't ping that because if I look at my routing table on my Linux machine, the route doesn't exist. All right, so let's quickly add some routes. And to achieve this, I'm just going to use the route add -net command on Linux now. On Windows, it's a bit different. And then I will add a route for the 192.0.0.0/30 network. And I will make, let's just check what the IP address is of this MikroTik router 1 that's connected to my intranet. So if I go to my addresses, 138. So I will then specify it is 192.168.149.138. I'll press enter and then operation not permitted, but it's because I'm not running this as sudo. So let's just do that. And now if I look at my route, I can see I've got a route for 192.0.0.0/30, which is this route on the left-hand side. And in theory, I should now be able to ping 192.0.0.1. Cool, I can ping that. Can I ping .2? That I cannot ping, but that's because router 2 is not aware of my routing, which is something we call return routes. But it's good that I can get to the router 1 address. Let's just add all of the other addresses. And I am adding these addresses on purpose because we will be talking about route aggregation in a separate video. I just want to add all of this so you can see how we're adding some static routes between our networks to get to places. But this is now just the Linux side. You'll see on the MikroTiks how quickly I can do it on there as well. So I'm just going to add 4. I might add 8. And then we just see my networks here is 10.0.0.0 and 10.1.0.0. All right, so that's quite straightforward. So all I'm going to do is type 10.0.0.0, 10.0.0.0.4, 10.0.0.0.8. Then I'll add the same routes for the red network, 4 and 0. So if I look at my routing table on my actual Linux machine on my computer, I can see I've added a bunch of static routes to get to these WAN IPs. So I'm basically telling my computer, if I want to get to any of those IPs, go to router 1. Now router 1 needs to also know how to get to those IPs. So if I look at router 1's IP addresses or IP routing table, we can see it knows how to get to the 192.0.0.0/30 and 192.0.0.4/30 subnets. but just because those are directly connected subnets or addresses. So what I'm going to do is I'm going to look at the routing table, and then I see for anything in the 10 subnet, so the 10 000/30, I'm going to basically route traffic from router 1 to router 2. So I'm going to route traffic to 192.0.0.2 from router 1. So let's add some routing. I'll say if I want to get to 10.0.0.0/30, use 192.0.0.2 as my gateway. And then I can quickly actually just copy this across. So there you can see it's an active and static route now. So I can just copy it, then change some of the details here just to get this quickly done. And now we have routes that exist from router 1 to push those routes to router 2. And then what I'd like to do is also similarly add routes from router 1 to the router 3 addresses, which is 10.1.00. Let's type 10.1.00/30, and that gateway is 192.0.0.6. I'll apply that, and that is just the IP address of router 3 on its Ether1 interface. All right, let's quickly just copy the rest. So I can make it 4 and .8, and I'll apply that. Cool, so now I have routes to my WAN links from router 1 to router 2, but it's still not going to work because I need return routing. I need a way to get back to my actual computer now. So what I'll do is I'll actually use a quick and easy way to do this. So I'll add routing on router 2 via the command line quickly. So I'll do IP route add destination. I'm going to add a default route, and I'm going to tell it its gateway will be 192.0.0.1. So basically I'm telling router 2 if it wants to get to any network, then use any network that's not defined in its routing table, use router 1 to get there. And I'll do the same on router 3, but let me do that via Winbox. So I'll change directory to downloads. I'll use Wine just to open up Winbox. And then I'm going to connect onto Ramon, and then I'll connect to my router 3. Cool. So now what I'll do is on router 3 on Winbox, let's just zoom in. If I look at the routing table, I can add a default route out quickly and say to get out to the internet or any network not defined in my routing table, use 192.0.0.5, which is in essence the IP address of router 1 on its Ether 3 interface that connects to my router 3. I'll click on apply. And now router 3 has a default route out as well. So I'm actually feeling pretty confident because I'm pretty certain now from my Linux machine and even the router. Let's try from router 1 and see if we can ping those WAN addresses. So from router 1, let's make sure, can I ping 10.0.0.1? I can. Can I ping 10.0.0.5 and .9? Because those are the WAN IPs on router 2 on its side. Let's see, can I ping 10.1.0.9? That I can ping. I can ping .5, and I should be able to ping .1. So those are the WAN IPs on Ether 2, 3, and 4 on router 3. Now, with that being said, my Linux machine should also now be able to get to those hosts, to those IPs. So let's quickly test it out and see. So I've got routes for it. And what I'll do is I'll run a ping to 10.0.0.1, and I'm getting response. That's actually really cool. So besides this, I'd actually like to run a trace route and see how the traffic is getting to those destinations. Because this is why trace route is such an awesome tool as well, because I can run a trace route to 10.0.0.1. Sorry, apparently I quickly just need to install this, so just bear with me. Install traceroute. This should be a quick install. Apologies. There we go. So let me try and run a traceroute again. And there we go. I run the traceroute, and basically what my machine is telling me, it's tracing to get to that IP. It's sending it to 192.168.149.138, which I statically set at the beginning. And then this hop then forwards it to its default gateway, which we are just not seeing in the routing table, but it is 10.0.0.1, which is that IP address for the WAN interface on Ether 2 of router 2. All right, and let's just see and make sure that it does the same thing if I traceroute to 10.1.0.1. And here you'll see it's actually going to a different path, where router 1 is then just sending it off to router 3. So that is very basic static routing. We've added some default routes. We've added specific static routes as well to say to which networks we want to get to. Before we end off the video, let's maybe just quickly add the same type of routes out to the intranet on all of these offices, and this will be quick. This we're just going to do an IP route add destination 000/0, specify our gateway, which is 10.0.0.1 in this case. I'm just going to copy this so we can do it a bit quicker. Admin blank. But my gateway is going to change in this case. Apparently my copy didn't take place, so let's just do IP route add destination equals NE gateway equals 10.0.0.5. And let's do the same on our last blue router. IP route add destination 0.0.0.0/0 gateway 10.0.0.9, which is the WAN IP of router 2 on Ether 4, its gateway. All right, and let's add the default routes on the red routers quickly. So IP route add destination 0.0.0/0 gateway 10.1.0.1, and the last one, or second last one, IP route add destination 0.0.0.0/0 gateway 10.1.0.5, and the last one, router 9, IP route add destination 0.0.0.0/0 gateway 10.1.0.9. Now I wonder, from my router 9, can I ping, let's say, 192.168.149.139. So that is failing. Can I ping 138? That I can ping, but that is the IP address of router 1, which is perfect. We should actually be able to break out to the internet now, but I know why it's not working, because we don't have any NAT rule out on router 1 yet. So let me just add a NAT rule out on router 1 just to prove that we've got internet access. So I'll just add a dirty quick one to say anything that's leaving out of Ether 1. We can masquerade that out. And if I look back at my table, we can see I've actually got internet breakout now. And this I've now set up actually on all of the devices in the topology. So each of the office can now break out to the internet with the static default routes we've implemented, and also the actual specific static routes that we've added. All right, I think this is where I want to end off the video. We're actually going quite long on this now. And in the next video, we'll be covering a bit more of the routing aspects, but we will also be looking at implementing policy-based routing, which is very fun to do. So I hope you've enjoyed the video, and I'll catch you guys in the next video. I'd like to thank my Patreon and YouTube members for helping the channel out, and I'll catch you in the next one. Bye, guys.